It could happen right now, in the heart of a distant, unnamed star, its nuclear fires suddenly snuffed out by an unseen force, or perhaps a billionth of a second from now, in the silent, empty space between your very atoms, a silent pop, the birth of a bubble. You wouldn't see it coming. You wouldn't feel a thing, because by the time you could, reality as you know it, the very fabric of existence, would already be gone. Imagine for a moment that our entire universe, everything we see, feel, touch, and understand, is like a single delicate bubble, shimmering precariously on the surface of some vast cosmic liquid. It's stable, yes. It holds its shape. It allows for galaxies to spin, and stars to burn, and life to bloom. But what if this bubble, our universe, isn't in its most stable form? What if there's a deeper, truer, more fundamental state of existence, a different kind of bubble, lurking just beyond the veil of our perception? This isn't the stuff of science fiction, though it feels like the ultimate cosmic horror story. This is a terrifying, plausible consequence of the standard model of particle physics, our most successful and robust theory of reality. We call our current state of a false vacuum. It's a bit like a ball resting in a shallow dip on a vast, undulating landscape. It's stable enough. It takes a nudge to dislodge it. But somewhere, perhaps far off, there's an even deeper valley, a true, absolute minimum energy state, a true vacuum. If, by some incredibly rare quantum fluke, a tiny ripple were to form in our universe, a microscopic seed of this true vacuum, it would be the beginning of the end. This isn't just a new kind of matter or a different dimension. It's a complete rewrite of the very rules that govern existence. This tiny nascent bubble of true vacuum would be born through a process called quantum tunneling. It's one of the most bizarre and counterintuitive phenomena in quantum mechanics, where particles can essentially teleport through energy barriers that they shouldn't have enough energy to cross. Think of it like a ghost passing through a wall. In the context of vacuum decay, it means that a region of space can spontaneously transition to this lower energy state, even without a massive energy input. And once that seed forms, it begins to grow. This bubble of true vacuum, once nucleated, would expand outward in all directions, relentlessly, at a speed indistinguishable from the speed of light. There would be no warning, no time to react, no way to escape. The light from an approaching bubble would reach us at the exact same moment its leading edge did. One instant, our universe. The next, gone. Erased, replaced. And what would be inside this expanding bubble? Not nothingness, but something utterly alien. The fundamental laws of physics would be rewritten. The very properties of particles and forces, governed by the omnipresent Higgs field, would change. Imagine a world where electrons have a different charge, where gravity pulls with a different strength, where light travels at a different speed, or where the strong nuclear force, which binds atomic nuclei, simply ceases to exist. Chemistry as we know it would be impossible. Stars would wink out. Planets would disintegrate. Life, in any form we could possibly comprehend, would be utterly obliterated. It's not just destruction. It's a fundamental alteration of the very nature of reality itself. This profound, terrifying possibility isn't some fringe theory cooked up by mad scientists. It emerges directly from the bedrock of modern physics, the standard model of particle physics. Specifically, it hinges on the precise masses of two of the universe's most fundamental particles, the Higgs boson and the top quark. The Higgs boson, discovered triumphantly at CERN's Large Hadron Collider in 2012, is the quantum excitation of the Higgs field, the invisible energy field that permeates all of space and gives other particles their mass. Its mass, measured to be approximately 125 GeV, is a critical piece of the puzzle. The top quark, the heaviest known elementary particle, with a mass around 175 GeV, also plays a crucial role. These two masses act like cosmic scales, delicately balanced. One tugs towards stability, the other towards instability. When physicists combine the measured values of the Higgs boson and top quark masses, the calculations suggest something startling. Our universe, the bubble we inhabit, appears to be in a metastable state. This means it's stable enough for now, but it's not in the absolute lowest energy state possible. It's like that ball in the shallow dip, perfectly content to stay there, but with the potential, however remote, to roll into that deeper valley. This isn't just an abstract mathematical exercise. The theoretical framework for vacuum decay was developed decades ago, in the 1970s, within the realm of quantum field theory. Visionary physicists like Sidney Coleman, alongside collaborators like Curtis Callan and Frank DeLucia, published groundbreaking papers, including the seminal The Fate of the False Vacuum. Their work laid the mathematical foundation for how this catastrophic decay would proceed. But for decades, it remained largely theoretical, a fascinating thought experiment. Because we lacked the crucial data, we didn't know the mass of the Higgs boson. The discovery of the Higgs boson in 2012 changed everything. Suddenly, physicists had the missing piece of the puzzle. They could plug the actual measured values into Coleman's equations and calculate the stability of our electroweak vacuum with unprecedented accuracy. The initial results, in the years immediately following 2012, were a jolt to the scientific community. The numbers suggested our universe was surprisingly close to the line between absolute stability and metastability, sparking intense theoretical interest and a renewed focus on this chilling possibility. And then, in a stunning breakthrough in January 2024, an international team of scientists announced the first experimental observation of an analog of false vacuum decay. Using a supercooled ferromagnetic superfluid of atoms, they created and observed bubbles of a true vacuum state, forming spontaneously. It wasn't our universe, of course, but it was tangible, empirical evidence for the bubble nucleation mechanism. Grounding this terrifying theory in the real world, it was a monumental step, bringing the abstract concept of cosmic annihilation into the laboratory. The idea that our universe could be a fragile, metastable bubble, poised to pop at any moment, is a staggering thought. It speaks to our cosmic insignificance, the profound mysteries woven into the fabric of reality, and the sheer unpredictability of existence. While the predicted timescales for a natural vacuum decay are mind-bogglingly long, estimates range from 10 to the 88th to 10 to the 241st years, vastly longer than the current age of the universe. The possibility remains. It's a silent, unseen threat that, if triggered, would render all of our human concerns, all of our triumphs and struggles, utterly meaningless in an instant. This ultimate ecological catastrophe wouldn't leave ruins. It would erase the very blueprints of existence. The silent pop we spoke of, that infinitesimal spark that could unravel everything, isn't some far-fetched fantasy cooked up by science fiction writers. It's a chilling possibility, born from the deepest theories of reality itself, a prospect that physicists have been grappling with for decades. To understand it, to truly grasp the profound implications of what a universe-ending bubble might be, we need to venture into the invisible architecture of our cosmos, to a realm where energy dictates destiny. Imagine, if you will, an unseen puppet master pulling the strings of reality, an omnipresent force that defines the very fabric of existence. This is, in essence, the Higgs field. It's not an empty void, but a cosmic ocean of energy permeating every inch of space, even the space between your atoms. Without this fundamental field, there would be no mass, no atoms, no stars, no us. Particles would zip around at the speed of light, unable to coalesce into the complex structures we see. It is the Higgs field that, through its interaction with elementary particles, bestows upon them their mass, giving form and substance to the universe. It is the ultimate source of both creation and potential destruction. But like any fundamental field in quantum mechanics, the Higgs field possesses a characteristic called potential energy. Think of it like a landscape, a cosmic topography that defines the most stable configurations of the field. Nature, in its infinite wisdom, always seeks the path of least resistance, the lowest energy state available. It's why water flows downhill, why a ball rolls to the bottom of a valley. For our universe, the Higgs field's potential energy determines the fundamental state of reality. Now, here's where the sombrero's shadow truly begins to cast its long existential pall. Visualize a grand, sweeping sombrero hat, lying brim down. The brim itself is wide and relatively flat, but it has a slight, shallow dip running around its circumference. In the very center, where the crown meets the brim, there's a much deeper, more profound depression, a true, absolute valley. This visual, known as the sombrero potential, is the most crucial metaphor for understanding our universe's perilous position. Our universe, as we experience it, is like a small marble-sized ball, resting in that shallow depth on the wide brim of the sombrero. This dip represents what physicists call a false vacuum state. It's stable, yes, but it's not the most stable state possible. It's like a temporary resting place, a local minimum in the energy landscape. Our reality, with all its galaxies, stars, and consciousness, is defined by the Higgs field, existing in this slightly elevated metastable state. We are comfortable, perhaps even complacent, in our cozy little dip, unaware that just a short distance away, metaphorically speaking, lies a far deeper, more energetically favorable state, the true center of the sombrero. That deep center, that absolute lowest point in the sombrero's potential, represents the true vacuum. If the universe were to exist in this true vacuum state, the fundamental laws of physics would be entirely different. The properties of particles and forces would be irrevocably rewritten. The staggering thought, the truly profound aha moment at the heart of this cosmic enigma, is that the very fabric of our existence, the reality you perceive right now, is defined by this invisible energy field. And our universe, our home, might not be in its most stable configuration. Reality as we know it could be temporary. We are, in a sense, living on borrowed time, perched precariously on the brim of a cosmic sombrero. What determines whether our universe is resting in this precarious false vacuum or the absolute true vacuum? It all comes down to a delicate cosmic balancing act, one dictated by the precise masses of two of the most fundamental particles, the Higgs boson and the top quark. Think of it as a cosmic scale, where the mass of the Higgs boson, measured at approximately 125 GeV, pulls one way, influencing the shape of the Higgs potential. On the other side, the top quark exerts a strong destabilizing effect. For decades, the precise nature of this balance was a mystery. Visionary physicists like Sidney Coleman laid down the mathematical foundations, theorizing about a phenomenon called bubble nucleation via quantum tunneling, but crucial data was missing. Then came a pivotal moment in 2012, the discovery of the Higgs boson at the Large Hadron Collider at CERN. This wasn't just another particle discovery. It was the missing piece of the puzzle. With the Higgs boson's mass finally measured, physicists could combine this critical data point with the already known mass of the top quark to perform the long-awaited calculations on the stability of the electroweak vacuum for the very first time. The results were electrifying and, frankly, a little terrifying. Initial calculations in the years following 2012 suggested that our universe was, surprisingly, very close to the line between being absolutely stable and merely metastable. It indicated that our marble on the sombrero's brim wasn't in a perfectly stable divot, but rather in a dip that, while comfortable for now, had the potential for a catastrophic roll into the true vacuum. So if our universe is in a false vacuum, how would it transition to this true vacuum? This brings us to one of the most bizarre and counterintuitive concepts in quantum mechanics: quantum tunneling. Quantum tunneling allows a particle, or in this case, a tiny region of space, to spontaneously pass through an energy barrier, as if our marble could vanish from its current dip and instantly reappear in the deeper valley, without ever having traversed the ridge in between. This is the mechanism by which a tiny bubble of true vacuum could spontaneously nucleate anywhere in the universe. It could happen in the heart of a distant star, within the cold void of intergalactic space, or even, theoretically, right here, right now. Once formed, this infinitesimal bubble of true vacuum would be self-sustaining. Its lower energy state would drive its expansion outward in all directions, at a speed that quickly approaches the speed of light, the ultimate cosmic speed limit. This means that if such a bubble were to form, its arrival would be impossible to predict, impossible to outrun. By the time any signal of its existence could reach us, it would already be here. Inside the bubble, the fundamental laws of physics would be rewritten. Chemistry as we know it would cease to exist. The very concept of stable atoms would likely vanish. It is, as some physicists describe it, the ultimate ecological catastrophe. For decades, this remained a purely theoretical construct. But then, in January 2024, an international team announced the first experimental observation of an analog of false vacuum decay. They meticulously crafted a miniature false vacuum in a lab. In this extreme environment, they observed the spontaneous formation of tiny bubbles of a true vacuum state, providing the first empirical evidence for the bubble nucleation mechanism. It was a monumental achievement, grounding a terrifying theory in real-world science. So, here we are, perched on the edge of the sombrero's brim. Our reality, a delicate balance of fundamental particles and unseen fields. We now understand the science, the metaphor, and even the experimental echoes of this profound concept. But what are the implications of living in such a potentially metastable universe? What does it mean for our future, for our understanding of cosmic time, and for the very definition of what is permanent? As we peer into the shadow of the sombrero, the questions only deepen. We left off gazing into the shadow of the sombrero, contemplating a universe that might be balanced on a knife edge, its very existence a temporary state. We grappled with the profound questions. What does it mean to live in a potentially metastable universe? These aren't just philosophical musings. They are questions born from the heart of modern physics. And the answers, it turns out, don't lie in ancient texts or grand celestial alignments, but in a cosmic detective story, one where the most crucial clues are almost impossibly small, yet hold the weight of all creation. Imagine, if you will, the universe as a vast, intricate crime scene. The crime, the potential for reality to simply end, not with a bang, but with a whisper, a silent pop. As cosmic detectives, we're searching for the culprit, or at least the conditions that could trigger such an event. Our investigation begins not in the furthest reaches of space, but in the smallest corners of existence, deep within the subatomic realm. For decades, physicists have understood that the stability of our vacuum is critically dependent on a delicate interplay between fundamental particles. The theoretical framework for this idea, this unsettling possibility of vacuum decay, was first laid out in the 1970s. Visionary physicists like Sidney Coleman, a brilliant mind from Harvard University, along with collaborators, began to sketch out the terrifying blueprints of how our universe might spontaneously tunnel. Their seminal papers, particularly The Fate of the False Vacuum, established the semi-classical theory, detailing how such a decay would proceed through something called bubble nucleation. They provided the mathematical scaffolding, the theoretical stage, but the crucial actors, the precise data points, were still missing. Fast forward to the 21st century, and the stage was set for the grand unveiling of these missing pieces. Our detective story takes us to two monumental scientific endeavors, Fermilab, in the prairies of Illinois, and CERN, nestled beneath the border of Switzerland and France. These aren't just laboratories, they are temples of discovery. At Fermilab, in 1995, after years of relentless searching, scientists unveiled one of the most elusive and massive particles ever discovered, the top quark. This isn't just any particle. It's the heaviest known elementary particle. Its immense mass was a revelation. Then, in 2012, came the moment that reverberated across the scientific world, the discovery of the Higgs boson at the Large Hadron Collider at CERN. This was the particle associated with the Higgs field, the omnipresent energy field that permeates all of reality, giving mass to fundamental particles. These two particles, the top quark and the Higgs boson, are the central figures in our cosmic drama. Their precise masses, measured with painstaking accuracy, are not just entries in a physics textbook. They are the cosmic clues that allow us to finally perform the calculations on the stability of the electroweak vacuum. Think of it like this. Imagine a colossal cosmic scale, so immense it balances the fate of all existence. On one side of this scale, we place the mass of the Higgs boson. At 125 GeV, the Higgs boson represents the stability of our universe. It's the anchor, the force that should keep us firmly rooted. But then, on the other side, we place the top quark. And this is where the plot thickens. The top quark, remember, is surprisingly heavy, significantly heavier than all other elementary particles. This immense mass pulls on the other side of our cosmic scale, tugging it precariously towards the metastable side. And here is the aha moment, the profound revelation. The ultimate fate of the cosmos hinges on the incredibly delicate balance between the masses of just these two subatomic particles. It's a staggering thought, isn't it? That the entirety of reality could be determined by the precise measurements of two microscopic entities. Initial calculations performed in the years following the Higgs discovery in 2012 sent a shiver through the physics community. They suggested something truly remarkable. Our universe was not comfortably stable, but surprisingly close to the line between being absolutely stable and merely metastable. It meant that our current vacuum, the state we perceive as reality, might not be the lowest possible energy state. It's like a ball resting in a shallow divot on a vast, undulating landscape with a much deeper valley, the true vacuum lying somewhere else. This metastable state means our universe is susceptible to decay, It's not an immediate threat, mind you. The predicted lifetime is extraordinarily long. We're talking about timescales ranging from 10 to the 88th to 10 to the 241st years. Numbers so vast they are almost incomprehensible. Many orders of magnitude longer than the current age of the universe itself. But the very existence of this possibility, this precarious balance, is what makes the story so compelling. It elevates these tiny particles, the Higgs boson and the top quark, from mere components of the Standard Model into the arbiters of our cosmic destiny. Their precise masses are not just data points, they are the cosmic dice roll. The energy scale, at which the Higgs potential is predicted to turn over and become unstable, is incredibly high, around 10 to the 10th to 10 to the 12th GeV, or even higher. This isn't an energy we can easily replicate in our accelerators, underscoring the theoretical nature of this particular apocalypse. It's a powerful narrative, this cosmic detective story. It shows us that even in the vastness of the universe, the most profound answers can be hidden in the smallest details. It connects the immense power of particle accelerators to the most fundamental questions about our existence. The scientists were, in essence, reading the cosmic tea leaves, and the implications of their discoveries are staggering. We are not just living in a universe. We are living in a specific state of a universe, a state that might be temporary. What other secrets are hidden in the masses of particles yet undiscovered, or in the subtle interactions we are only just beginning to comprehend? This journey into the heart of particle physics, this exploration of the universe's delicate balance, is a testament to the human spirit of inquiry. It's about our relentless drive to understand not just what we are, but where we are in the grand scheme of cosmic existence. So, we have our clues. The Higgs boson, pulling towards stability. The top quark, tugging towards metastability. We have our cosmic scale, hovering precariously. The discovery of these particles allowed physicists to move beyond pure speculation, to begin to quantify the universe's stability, or lack thereof. But what does a decay actually look like? What happens when that delicate balance finally tips? What kind of reality would replace the one we know? The next chapter of our cosmic mystery takes us from the precise measurements of particles to the terrifying light-speed expansion of an entirely new reality. We stand on the precipice of a cosmic mystery, one where the very fabric of our reality hangs in a delicate balance. The Higgs boson, a beacon of stability, and the top quark, a harbinger of potential decay, continually tug at the scales of our universe's existence. We've seen how the precise measurements of their masses, painstakingly gathered at facilities like the Large Hadron Collider, allowed physicists to move beyond pure speculation, to begin quantifying whether our universe is truly stable or merely metastable. But to truly grasp the profound implications of this cosmic tightrope walk, we need to understand what decay actually entails. What happens when that delicate balance finally tips? What kind of reality would replace the one we know? The journey continues, taking us from the invisible dance of particles to the terrifying light-speed expansion of an entirely new reality. It forces us to confront not just the end of our world, but the fundamental rewriting of the laws of physics themselves. For decades, the concept of a universe teetering on the edge of oblivion remained largely in the realm of theoretical physics, a beautiful but terrifying mathematical construct. It began to take shape in the 1970s within the intricate framework of quantum field theory. Visionaries like Sidney Coleman, a brilliant and imaginative theorist at Harvard University, along with his collaborators Curtis Callan and Frank DeLucia, dared to contemplate the ultimate death of reality. Their seminal papers, including the profoundly influential The Fate of the False Vacuum, laid the mathematical foundation for understanding how such a decay might actually proceed. They introduced us to the chilling idea that our universe might exist in a false vacuum state. Imagine, if you will, a vast cosmic landscape of energy. Our universe is like a ball resting in a shallow divot on this landscape. It's stable, yes, but only relatively so. There's a deeper, more profound valley somewhere else, a true vacuum, representing an even more stable, lower energy state. For our universe to transition to this true vacuum, it wouldn't simply roll over. Instead, it would need to undergo a bizarre quantum phenomenon known as quantum tunneling. Think of it as spontaneously passing through an energy barrier rather than climbing over it. In this context, quantum tunneling would allow a tiny, infinitesimal region of this true vacuum to spontaneously materialize, a process known as bubble nucleation. This theoretical framework, while compelling, remained purely speculative for decades. It wasn't until the monumental discovery of the Higgs boson at the Large Hadron Collider in 2012 that humanity gained the crucial data point needed to transform these abstract equations into something potentially quantifiable. With the Higgs boson's mass measured at approximately 125 GeV and the top quark's mass already known to be around 173–175 GeV, physicists finally had the key values to calculate the stability of the electroweak vacuum for the first time. Initial calculations in the years following 2012 painted a disquieting picture. Our universe seemed to be surprisingly close to the line between absolute stability and a precarious metastability. But even with these precise measurements, the concept of a quantum field decaying or a bubble of new reality spontaneously forming remained incredibly difficult to grasp. How do you visualize something so abstract, so far removed from our everyday experience? How do you truly feel the weight of a theoretical apocalypse when its mechanism is hidden in the subatomic realm, unfolding across timescales incomprehensibly vast? This was the ultimate challenge for scientists, to bridge the gap between complex mathematics and a tangible, observable phenomenon. For nearly 50 years, the idea of vacuum decay was a chilling ghost story whispered among physicists, a mathematical possibility without a witness. Then, in January of 2024, the whispers stopped. The theoretical ghost story found its first undeniable analog in the real world. A groundbreaking announcement sent ripples through the scientific community. An international team of scientists had achieved something truly remarkable. For the very first time, they had experimentally observed an analog of false vacuum decay in a laboratory setting. This was no longer just abstract mathematics confined to theoretical papers. It was a tangible, observable event. The core mechanism, the spontaneous birth and expansion of a bubble of a more stable state, had been witnessed. The cosmic threat, once an intellectual curiosity, suddenly felt startlingly, undeniably real. Imagine for a moment creating a universe in a bottle. Not a universe of stars and galaxies, but a microscopic quantum realm, meticulously crafted and controlled. That's precisely what these pioneering researchers, supported by institutions like the University of Trento and Newcastle University, set out to do. Their canvas was far more subtle, yet equally profound. A supercooled ferromagnetic superfluid of atoms. They took a gas of atoms and chilled it down to an unimaginable extreme, to a temperature of less than 1 microkelvin, which is a millionth of a degree above absolute zero. At these frigid temperatures, quantum effects dominate, and the atoms behave less like individual particles and more like a single coherent wave. By precisely tuning magnetic fields, the scientists were able to coerce this ultra-cold gas into a state that perfectly mimicked the false vacuum of our own universe. It was a fragile, metastable state, delicately balanced, just like the one our cosmos is theorized to inhabit. They had, in essence, built a controlled toy universe, a miniature replica of cosmic uncertainty contained within the confines of their lab. And then, they waited. Like cosmic observers peering into an alternate reality, they watched. What they witnessed was nothing short of astonishing. Spontaneously, without any external trigger, tiny bubbles began to form within this supercooled false vacuum. These weren't bubbles of air or steam. They were regions where the atoms had suddenly reconfigured themselves into a lower, more stable energy state, an analog of the true vacuum. These nascent bubbles didn't just appear and vanish, they expanded. They grew outward in all directions, consuming the surrounding false vacuum. The scientists had captured, in exquisite detail, the very mechanism Sidney Coleman and his collaborators had theorized decades ago. The spontaneous formation of a more stable state, followed by its relentless expansion. It was a mesmerizing, almost terrifying display of quantum mechanics at play, compressed into a laboratory setting. This wasn't a simulation. It was a real physical manifestation of a process that could, theoretically, one day, reshape our entire cosmos. This experiment, this bubble in a bottle, isn't just a scientific curiosity. It's a profound validation. It proves that the core mechanism behind vacuum decay, the spontaneous nucleation and expansion of a bubble of a more stable reality, isn't merely a theoretical abstraction. It's a phenomenon that can and does occur in specific physical systems. For the first time, we have empirical evidence, a tangible model, for what might be the ultimate ecological catastrophe. Think about the implications. Our universe, a vast tapestry woven from specific fundamental laws, exists because the Higgs field has a particular shape, a specific energy minimum. But if a true vacuum bubble were to form, the Higgs field inside that bubble would roll to its true lower energy state. This isn't just a slight alteration. It would fundamentally rewrite the laws of physics. The properties of particles would change. The forces that govern matter, the very rules that allow atoms to form, stars to ignite, and life to exist, they would all be different inside that expanding bubble. Our chemistry, our biology, our entire known reality would become impossible. This experiment, by showing us the how, makes that cosmic threat feel chillingly, undeniably real, even if it's on a vastly different scale. It takes the philosophical terror of cosmic insignificance and grounds it in observable science, connecting directly to our primal fears of annihilation and the unknown. Now, it's crucial to put this into perspective. While the 2024 experiment provided the first empirical evidence for the mechanism of vacuum decay, it did so in a highly controlled, microscopic environment. Our universe is not a supercooled gas in a lab, and the timescales involved are vastly different. When we talk about cosmic vacuum decay, we're not talking about minutes or hours. We're talking about timescales so immense they defy human comprehension. Calculations suggest that even if our universe is metastable, its predicted lifetime could range from 10 to the 88th to 10 to the 251st years, many, many orders of magnitude longer than the current age of the universe itself. So, while the existential terror is potent, the thought that it could happen right now, the scientific consensus is that a naturally occurring vacuum decay is an extraordinarily rare event, if it ever happens at all. The beauty of the 2024 experiment isn't in predicting when our universe might end, but in showing us, with tangible clarity, how such a profound transformation of reality could unfold. The next chapter delves into the terrifying specifics of this cosmic rewrite, exploring the physics of a universe fundamentally altered. The aha moment of the 2024 experiment has brought the abstract concept of vacuum decay out of the purely theoretical shadows and into a realm of tangible, observable science. We've witnessed in a controlled toy universe the birth and expansion of a true vacuum bubble. But this raises even more profound questions. What would it really be like inside such a bubble? What new laws of physics would govern a universe reborn from the ashes of our own? And what does it mean for us, fragile beings on a small blue planet, to contemplate an end not just to life, but to the very rules that permit our existence? The thought is chilling, isn't it? That the very fabric of reality, the bedrock of everything you know and experience, could fundamentally change, instantly, irreversibly. The idea that the universe might come with a self-destruct button, pressed without warning, rewriting chemistry and life itself, is the ultimate cosmic horror. It's a vision of an end so complete, so absolute, that it transcends any mere apocalypse. But before you let that chilling image take root too deeply, let's take a breath. Because while the science of vacuum decay is real, and the implications are profound, the timeline for such an event offers us a cosmic reprieve, a breathtaking expanse of time that shifts our perspective from immediate dread to profound awe. Our journey into the false vacuum has shown us that our universe may exist in a state of delicate balance, stable, yes, but not ultimately stable. Imagine a ball resting in a shallow divot on a vast, undulating landscape. It's comfortable there. It takes effort to push it out. But given enough time, or a strong enough nudge, it could roll into a deeper, more stable valley. This is the essence of a metastable state, stable for now, but susceptible to decay to a lower energy state, a true vacuum. This concept, central to quantum field theory, posits that the quantum fields permeating our universe, including the all-important Higgs field, might not be in their lowest possible energy configuration. If a tiny bubble of this true vacuum were to nucleate anywhere through a bizarre quantum phenomenon called quantum tunneling, it would expand at nearly the speed of light, transforming everything in its path. Imagine for a moment stepping across that invisible, expanding wall. Inside the bubble, the universe isn't simply devoid of life. It's devoid of the possibility of life as we understand it. The fundamental forces that orchestrate the cosmos, gravity, electromagnetism, the strong and weak nuclear forces, they wouldn't just be altered, they'd be entirely reconfigured. The Higgs field, that pervasive ocean of energy that grants particles their mass, would settle into its new lower energy state. This isn't a subtle tweak, it's a cosmic upheaval. Consider the atoms that make up your hand, the air you breathe, the light from distant galaxies. Their very nature is defined by the precise masses of elementary particles, masses that are dictated by their interaction with the Higgs field. If the Higgs field shifts to a true vacuum state, these masses would change dramatically. An electron might become many times heavier, or perhaps impossibly light. Protons and neutrons, the building blocks of atomic nuclei, could become unstable, decaying into exotic new forms of matter, or simply ceasing to exist as stable entities. Without stable protons and neutrons, there are no atomic nuclei. Without atomic nuclei, there are no atoms. Without atoms, there is no chemistry. The vibrant tapestry of the cosmos woven from the intricate dance of particles and forces, would unravel, replaced by an alien, incomprehensible void. It's the ultimate ecological catastrophe, not because it eradicates species, but because it annihilates the very framework within which species could ever arise. The universe inside the bubble would be a sterile, fundamentally different realm, where the constants of nature we've painstakingly measured would be mere echoes of a forgotten reality. It would be a place where light might behave differently, where space and time might warp in unfamiliar ways, where the very definitions of energy and matter are radically redefined. You wouldn't just cease to exist. The very rules that allowed your existence would be erased. This profound, terrifying possibility forces us to confront a deeper truth. If our universe, with all its intricate beauty, is merely a temporary fluctuation, what then? Does it diminish our existence? Or does it perhaps expand our understanding of what existence truly is? Imagine the cosmos not as a singular monolithic entity, but as an infinite churning ocean of possibility, a cosmic foam. Each bubble in this foam represents a different universe, a different set of physical laws, a different manifestation of reality. Our universe, the one you and I inhabit, with its particular Higgs boson mass, its specific top quark mass, its unique constants, is just one such bubble. A vibrant, complex, yet ultimately metastable bubble, floating alongside countless others. This isn't just a poetic analogy. It's a concept deeply rooted in modern cosmology, particularly in theories of the multiverse. The idea that our universe might have been born from the decay of a different false vacuum state during cosmic inflation already hints at this grander tapestry. So, when we speak of vacuum decay, perhaps we are not witnessing the end, but rather a transformation within this grander, infinite cosmic foam. The collapse of our metastable vacuum wouldn't be the cessation of all reality, but merely the bursting of our particular bubble. This is the ultimate aha moment, the realization that the end of everything we know might not be the end. It could be a transformation into a new, alien reality we cannot comprehend. Our existence, our universe, could be just one chapter in an infinite cosmic story. Think about it. The very act that would erase our universe is itself a process of finding a more stable, lower energy state. In a strange, almost paradoxical way, vacuum decay could be seen not just as an act of destruction, but as an act of cosmic creativity. This perspective doesn't diminish the profundity of our own reality. On the contrary, it imbues it with an even greater sense of preciousness and wonder. To know that our existence is a unique, perhaps fleeting expression of the universe's potential only amplifies its value. How do we, as conscious beings, grapple with such an ultimate, uncontrollable risk? How do we find meaning when the very ground beneath our feet, the very laws that allow us to exist, could theoretically shift without warning? The answers are deeply personal, yet universally human. Some might find solace in the incredibly long timescales involved, the billions upon billions of years that statistically separate us from such an event. A risk so remote, it remains purely theoretical for our practical lives. Others might find a renewed urgency to cherish the present, to marvel at the fleeting miracle of existence in this particular universe, knowing its potential impermanence. The awareness of vacuum decay, therefore, becomes not a paralyzing fear, but a profound catalyst for contemplation. Consider the implications if our universe is indeed just one bubble in a cosmic foam. What if, across the infinite expanse of this multiverse, countless other vacuum decay events are constantly occurring, each one collapsing an old reality and giving rise to a new one? This concept resonates with theories of cosmic inflation. Our very own universe might owe its genesis to a vacuum decay event. The death of one vacuum state becomes the birth of another. The universe, in this grander vision, is not static, not fixed. It is a dynamic, ever-changing entity, constantly exploring the myriad possibilities of physical laws. Our specific laws are merely one manifestation among an infinite number of potential realities. So the ultimate question isn't, will our universe end? But rather, is our existence just one chapter in an infinite cosmic story? This question shifts the focus from an individual, finite end to a boundless, ongoing narrative. We are like characters in a single act of a play that has been running for an eternity. The death of our particular universe, then, becomes less of a final curtain and more of a scene transition, a metamorphosis into a reality that is currently beyond our comprehension. This philosophical leap from a single vulnerable universe to an infinite transforming multiverse is perhaps the most profound implication of vacuum decay theory. It transforms a terrifying scientific possibility into a catalyst for profound cosmic awe. The journey of understanding vacuum decay is a testament to the power of human curiosity. From the abstract equations of Sidney Coleman in the 1970s to the pivotal discovery of the Higgs boson at CERN in 2012, to the groundbreaking experimental analogs observed in 2024, humanity has dared to peer into the deepest recesses of physical reality. And in doing so, we've stumbled upon a concept that transcends mere physics. It's a concept that suggests continuity beyond destruction, creation through transformation, and an endless cosmic narrative far grander than any single story we could ever conceive. The possibility of vacuum decay, therefore, becomes a lens through which we can explore the very nature of reality, existence, and our fleeting yet precious place within it. It's a reminder that even in the most terrifying scientific predictions, there can be found a profound sense of wonder. What if our universe, despite its apparent stability, is destined to give way to another vastly different reality? And what if, in that grand, ceaseless transformation, the end of our story is merely the beginning of another, in a universe utterly beyond our wildest dreams?